we're going to take our last lecture regarding applications. And I decided to put it after DNS because what we'll see that here, the purpose of those stuff is to do what? Is to be able to let a client, such as your computer, connect to another client without actually moving, without needing a name. So we'll see how it happens. Anyway, so we are still at the application level, all right? Be aware that this is the last one. Today, most of the examples that I took was the same. They are the same with the textbook, meaning that this is about file sharing, though peer-to-peer systems are not only for file sharing. But file sharing is one of the main examples, all right? It's what makes peer-to-peer very popular across the internet. The very first application designed for peer-to-peer file sharing was introduced back in 1999. It was an undergrad student, and in 1 year, he got 100 million users. So you see, so that was really big at that time. So we're going to take those examples. We're going to see three of them, including a fourth one, which is Bittorrent. So we're going to see Napster, Gnutella, Kazaa, and Bittorrent. So Kazaa, for instance, is very famous because those are the guys who also wrote Skype. Skype is the same company with the guys who did Kazaa. So you see, so they've been quite successful. Wow. And finally, we're going to introduce the overlay networks because everything is also implemented like this. I won't have time to go over Cord. I don't think so. So I may have to skip the slides regarding Cord. You can read in the textbook, they have a section, but there won't be any assignment or homework regarding Cord, all right? So there are a few slides that you may read. If I don't have time to go over this, doesn't matter. You're going to see that as a graduate student, but I'd rather introduce the overlay networks. So let's start. So once again, as we said, okay, so we have most of the applications, okay, that we know by now, which is like, for instance, a web. We assume that we have a server, and the servers are quite specific, given that they're also end host, but they're always on. They have an IP address which actually doesn't change that much, all right? So it's static, it's not dynamic. They have a name that we are supposed to know as a client. So we can either find the name by doing a Google, so keywords in Google, we get a name. And as well, we have port numbers, but those port numbers are well known given the service. So if I try to connect to a web server, we know that he's probably listening on the port 80. Okay, so those are well known. So we don't need any resolution here. On the other side, we have the clients. The clients are connected intermittently, which means that sometimes they may be on, sometimes they may be off, right? There's no requirement on the client. They just connect to send a request, get the response, and that's it. They may disappear, right? Then we have the fact that they have a dynamic IP. Yes, when we connect with DHCP, our IP may change, even at home or from a coffee shop or wherever. So the IP address of a client depends on its location. It depends on the time of the day, all right? So I could have an IP address for an hour. It may change later. Their names are not known to the DNS. So if you're home and you have an host, your laptop doesn't appear in the DNS. So there's no way someone may connect you by knowing your name. They need to know the IP address. So that's a pain in the neck. But basically, in those kind of applications, there's no reason why a client we should connect to another client. We should go always through a server, right? And the port numbers, they are random, okay? So there's not specific value with any specific meaning. We can have a random value. So those are for the client server application. And oh yeah, because I forgot this one, yeah. So, and then we have the peer-to-peer application. And what is new with the peer-to-peer application is the fact that any end host could be a peer. So what do we mean by peer? It means that I may be a client, or I may act also as a server. So which means that other peers who are equal to me, so everybody's running the same program, which is not the case for the client server, since we have a browser and the web server on the other side. In that case, we have one single program, is the same. And one of the problems of having this is we don't involve any server, specifically dedicated server. We only have clients, which means that the clients have some bad properties, meaning the IPs are changing and they may not be connected all the time. All right, so that's one of the problems. So what we'll see when we do file sharing, so at some point we may be the one downloading a file, but later we may be the very client, a peer, who will offer that client to somebody else and upload it to somebody else. So it means that I may be downloading, but as well at the same time offering the file to somebody else. So one of the problems now is since we have no names, the port numbers may be random. The IP address may change over hour. So one of the questions for the peer-to-peer application is how to discover the IP address of a peer. So how can I know about anybody else? And what is more, this will probably depend on the type of service that is offered. So for instance, if I'm doing file sharing, I need to know what is the file I'm looking for, and giving the file, I may know the IP addresses of the peers. So there are many ways of doing this, so we're going to see a few examples regarding this. But basically, it's going to be pretty much the same. We have a database, which may be distributed, and we're going to query this database, depending on the service. Could be the file, MP3 file, could be a movie, and somebody needs to respond with the IP address of the peers. Very basic, okay? But in any case, we can use DNS. Even though DNS have been always, okay, the way to go to find somebody else who we want to connect to if we don't know the IP address. All right, so once again, the basic information here is, once again, what we send is a message with multiple headers, the link layer header, IP header, transport header, and we need to fill the information here. So usually, thanks to the keywords that we submit to Google, for instance, we get the name. Based on the name, we use DNS to get the IP address. The port number is given by the application. So if I'm using my browser, the browser will say that, okay, the request needs to be sent to the port 80. Okay. So we can see that it's quite easy here, based on the DNS, to fill part of the headers that need to be filled. When we move now for the peer-to-peer, there's not just a CAN system. There's no way we can learn the IP address through DNS. We need to find another way, and the same for the port number. So how can we know those two informations here? Okay, so this is what we're trying to solve. All right, so the peer discovery, there are few ways of doing this, which are pretty straightforward. The first way is to say that we may have a directory based. So what does it mean? We have a server somewhere. Oh, I'm sorry. So it's peer-to-peer, but we have a server. Let's try to explain why it's still considered peer-to-peer. So first of all, when you are a peer, we're going to join the server. And when we join, we're going to basically register by providing the list of the files that we want to share. So everything going to be uploaded in that server, in the database. It's going to be updated. So it means that now we're going to organize the database, such as for one file that has been published, we know the IP address of the peers who are sharing this one when they join. So now when we want to do a search, we only submit the search to the server, and then the server will return a list of IP addresses for the given file for any peer who is actually sharing that one. Pretty simple. So why is it peer-to-peer? Because obviously when we're going to download, do we need to go through the server to download? We don't need. We can pick one of them, right? One in the list, and start downloading without having the information, without involving the client anymore, right? So the server will basically give us the IP and input, but we also have the port number, right? So the peer have the IP and the port number thanks to the server. So pretty simple. So all you need is to maintain such a server somewhere. Okay, very simple. And then we do the fetch, and as I said, so fetching the file is peer-to-peer. So the only thing that happens peer-to-peer here is the fact that I download without using the server. But everything related to publish, joining, and search goes through a client-server architecture. Obviously, here the IP may be hard-coded, inside the application. When I download it, I know the name or the IP address of the servers, so I don't need to do DNS anymore to learn about the server. The other way of doing this is another way which is quite brutal, but we remove the requirement of a server. And what's going to happen in that case? It means that, first of all, I need to connect to other peers. So it means that at some point, I may discover about other peers who are running the same application. So the thing about this is, how can I have such a list? Well, we'll see. And doing so, it means that by discovering a few other peers, I may connect, and I have a random here graph where any peers are connected together. So it may be a mesh network, but otherwise there will be too many connections. But actually we have such a structure that is built out of discovering about other peers. And whenever I need to send a search, I will flout the rest of the network looking for a file. So the request is going to go everywhere in that network, okay, between the connection between the peers, and I'm going to find eventually someone who is sharing the file. And based on that file, all I need to do is he's going to reply to me. Sorry, I didn't do that, but anyway, somebody going to reply. And knowing the IP of this guy, I may start downloading. Okay, so two main approaches. All right. So let's get into the details of what applications are running those kind of models. So but first, before, let's try to see why is it powerful to use peer-to-peer for file sharing. So let's say you have a file here, and the size of the file is f bits. And here, what do we have? We have the uploading rate and the downloading rate at the different peers. So if we do client server, what's going to happen here is the fact that, first of all, if we have 1, 2, 3, 4 peers that need to download the same file, and if the size of the file is f, in total, the amount of bytes that I need to send is for f. So you see, so as you increase the number of receivers, okay, you will need at the server to send a huge amount of bytes. So which means that if I look at the time that it takes to send the data to all the peers, given that here I put n equal 4, you can see that in that case, it will take n times f divided by the uploading rate. Of course, we may also consider that maybe the bottleneck of the system is the downloading rate. So somebody going to slow down the server. So it means that either I have US larger than UDI, but if it's the opposite, in that case, I should consider that this is the bottleneck. So that's the reason I may have this one here or this one here. So in all case scenario, it will be the max in order to send to everybody else. All right. So that's the reason we always consider that either the server have enough uploading and the downloading won't delay, won't introduce a latency, or the opposite. So now, if we want to speed up the process, we don't have too many ways of doing this. So either I can increase the sending rate of the server, but that costs money. I may increase the number of servers. So I may say that, well, one is not enough. So let's add some mirrors, such as you multiply the US by as many servers as you have. So you increase the uploading rate, okay? So it will take less time sending the same quantity. But in both cases, you need to deploy extra infrastructure, either through more bandwidth or through more servers. And that costs money. And maybe you don't have this money available. So another way of doing this, and that's the reason peer-to-peer is very powerful, is to say that, okay, so in order to offload a little bit of the load on the servers, I'm going to use the receivers themselves. So what does it mean? It means that once the receiver gets a coffee, he may start sending to other receivers as well, such as you can reduce the overload on the server. So what's going to happen now in this case, you may see that I've added also the uploading rate at the different peers. Oops, this one was not part of it, but anyway. So now you may see that the sending capacity of the system is not only US for the server, but is as well the operating rates coming from all the other peers, right? And as you may see, as you increase the number of receivers, you increase the number of the capacity of the network. And what is beautiful about this is self-scalable. Why? Because the more receivers, the less overload. So that's very nice, right? So it's really self-scalable. So if we look at the formulas now, okay, so once again, the server may send it, but not only the servers, okay? We also have the other uploading rates. So where is it in the formula? I cannot see here. Yes, the uploading now is here, is the servers plus the other peers. And now I can complete the formula by saying that either the server needs to send one first copy, the slowest receiver are the ones who's going to delay the whole system. So we may consider that all the receivers are not equal, and then one of them who is really slow into getting the server. So this is very important because in one of the questions in the assignment, when I ask about how much time does it take, you're always going to make the assumption that, okay, everybody get it on time, but there's a last one who is very slow into getting it. So this is a upper bound, as we may not have the precise data, but just giving an upper bound is enough. So if I plot now, oops, where is this? Oh, there's no, oh, too bad anyway. So if we plot, I think that there's a plot somewhere, but anyway. So if I look at client server goes this way, as I increase the number of receivers, it means that it's going to slow down, it doesn't scale. And if I plot this kind of formula, it's going to give me for peer-to-peer something that is log-based. And as you may see, having log is really good for scalability because as you increase, the overload on the system or the time that it takes to download is limited, is bounded. So there's very nice systems, okay? Anyway. So file sharing application can be classified according to what we said before. So they may be centralized, so they need a server. This is what we're going to see with Napster. We may also do something that is hierarchical, so it's in between the decentralized and the centralized. So we're going to try to explain. So this is like hybrid, okay? And in all cases, what we need is to be able to locate a content, okay? And sometimes we will see that we can do some parallel downloading as well by splitting the file. So we're going to see all those techniques to improve even the system, all right? So we're going to go through all those categories. Okay, so yes, I already said that the peers are self-scaling, okay? So it may be very good for scalability, but we have some reality here that we may take into account. First of all peers are not in the system. So it means that when we say that we have n of them, it's a very strong assumption because keeping the peers in the system, we know that it doesn't going to happen. And it can also happen because they IP change. So once they change the IP, they disappear of the system. So they need to join again the system, and it takes time. Right? So yes, n is not fixed. The number of peers may change. We need to find each other. And what is more, we need to know exactly who is willing to share a file. And this is the incentive. So incentive is a big issue in peer-to-peer systems, right? So somebody who download the file may have enough incentives in order to share it to other ones. Okay, so here is the final graph that I wanted to show you. So yeah, so here this is like a log-based, which is very something that in computer science we're looking for, because as you may see, it's scalable, okay? You may add new nodes in your system. It doesn't gonna add more latency. So this is very interesting. Okay, so the challenge is, as I said, is how to localize the peers in your system, okay? So first of all, we need to know who is online, and out of those who are online, we need to know who is sharing some content. And if there are many of them, what is another thing that we may want to do as well? We want to find the good peers. And what do we mean by good peers? Someone who have a good sending rate. Okay, as I want to get the file as fast as possible. So there may be also a third criteria here, which may be good. So it's challenging because the peers may come and go. Yes, of course. And even when they leave, as I said, they may come back in the system with a different IP. And if IP is used as an identifier, in that case, I may not remember who is that peer. And of course, the incentive, so how to keep the peers as long as possible in the system, okay? And this is basically Bittorrent is the best into providing incentive to the system. So that's the reason I introduced Bittorrent as well, because it's one of the very, very strong proposals that will give a very strong incentives for the people, not only to stay in the system, but to give as much of their bandwidth to others. All right. So as I said, so for localizing the peers, we will go through three main examples as a beginning: Napster, Gnutella, and Kazaa. Okay. And the goals here is to make it scalable, to keep it simple, robust, which means that if I have a peer that leaves, the system need to survive. And also something that very interesting is to be able to deny that actually my software is used for bad things. All right, because for instance, Napster only lasted for a year before they disappeared. Right, they were closed. They were crippled by so many fines they needed to pay that they finally gave up. Okay, so Napster was born in the beginning of 1999. Okay, and yeah, and if you look after 1 year, they gain like 80 million users, which is huge, right? I mean, this is like a killer app. And but obviously, yeah, starting from there, they have to close, all right, and they close business because of the lawsuits. And one of the main problems is due to the fact that they needed a server. So let's get into the details. So this is a capture of, for those who used it in the past, but I know that 2000 is maybe too far away from you guys. But yeah, it was pretty simple. I mean, it was just a search with a list of peers for a given name, right? So you just put, and that was only for music files. All right. So as I said, pretty simple. One software, you download the software, you create an account, password, username, and so on. Included in the software, we used to know the name of the server, which was hard-coded in the application. And so the first thing that we need to do, obviously, is to first contact the server. Not for that reason, anyway. So where is this? I think that it's upside down. So let me see. Okay. So there's a publish first. So there's a join anyway. So you just join a first time, but you need only one. You create an account, and then you keep publishing and updating the list of the files that you are sharing. So based on this, the server will have a kind of a directory where for a given file, he knows whoever is sharing. And basically, when you do the publish, then later you can send a request. And what you receive in the reply is the IP and the port number. And then you may start downloading from whoever you want in the system. Okay? So the main problem was the server. And they couldn't deny because the lawsuit was about Napster running those servers. Okay? So the properties was you need to continue updating the file because as you download the more files, you need to update the list of files that you were sharing. Okay. The only thing that was peer-to-peer was the file transfer. So the server was not participating to this. And even though it was maybe enough to deny any implication in case of legal action, that was not enough because that's the reason they closed. So it was a proprietary protocol, so it means that there were only one software available. So the protocol was not open, so we couldn't design multiple clients. And obviously, we couldn't know who is a good peer in order to classify the peers and know who is a good peer out of them. So the list was a little random. So once again, one of the limitations, as I said, we have a server. So the server is a single point of failure. It's a bottleneck because too many requests, too many updates. So the server was overwhelmed, okay? And what is more, the server was a problem with the lawsuits, okay? So that's the reason 1 year later, people thought about doing another system. The system was called Gnutella. And what is Gnutella? It appeared in 2000. It was totally open, so many different clients were designed. So the protocol was specified by those guys. But then many clients like Morpheus, LimeWire, BSHare, all of them use the Gnutella protocol. Okay. And it's pretty simple. There's no publish at all. So all you need is to try to join to find other peers in the system. So that is really, really challenging. And then when you do the search, you just flout, all right? And once you get the IP of the peer who is sharing what you're looking for, all you need is to fetch. So very simple. So it's fully distributed, no central server. It's a public protocol, open source. So many client. One of the biggest issue is the bootstrap. How do you bootstrap? Because as I will show you here, well, to join, I will show you in the picture, right? It's easier. So the first thing that you need to know before you send the query is to know who are your neighbors. So let's say you want to design such a system. What would you do in order to have 100% distributed without server, in order to discover other nodes in the internet who is running a given protocol or a given software? They start with the very first IP, 0.0.0.0, and they continue and they scan all the IPs of the internet. And so you start, and it may take like days before you reach one IP address that actually have somebody running Gnutella as well. So you may start sending a lot of discovery messages across the internet, and you have 2 power 32 IP addresses, and you need to scan all of them. But this is fully distributed. The same way, if you want to make calls and you don't know who you want to call, you take random numbers, as you said. But in that case, they use like some blocks, and they start, pinging, connecting to all of them. So yeah, it used to take a lot of time. Obviously, they cheated at some point because there were some well-known list of peers, quite stable peers, that may be used. So you could download those files on the internet from a web server with an updated list of nodes that you may start connecting to from the start, and that will give you the very first connection that you could have at the beginning. Okay, so a list of candidates. But if you don't have such a list, no other way, you start scanning all the IP addresses in the world. Yeah, that's pretty brutal. But if you think about it, you have no other way of doing this, right? And given that if you start scanning, yeah, you may be flagged, and probably if you're running, for instance, a node at the university, they're going to see this kind of behavior because it's really easy to detect behaviors where either you scan port numbers or IP addresses. Okay, so be careful because yeah, you may be flagged. So that's the reason they started using the word cheating. They have a check list of peers that they may start with. But once you do your first connection to some peers, then if you need to send a query, you just flood the query everywhere and you wait for the answer. So the bad thing about this is it's not like when you ask a server, you have a round trip to the server that is limited, right? You know basically the upper bound to the RTT. In our case, all depend on how far should your query travel. So it means that the time to resolve the query is not bounded. And that was also another problem, okay? Anyway, so here, once I know the IP and the port number, I may start downloading, okay? So no publish, no available list of any file shared. I need to discover the peers and discover whoever is sharing a file that I'm looking for, right? But the good thing about this kind of graph is a totally random graph. So actually you have the degrees are heavily, there's a heavy number of connections, which make it super robust, which means that even if you lose a peer, you have like a bunch of other nodes in your neighborhood that you may start with. Anyway, you understand the basic idea. Here, one of the problems is by doing flouting for the request. If you have also some loops in your system, there's a problem because then you're going to overload your system with queries. But we don't really have a choice because here the topology of the network is totally random. Okay, so the advantage is fully decentralized, even though you may cheat with a list of candidates for your peers. The search cost is super heavy as well, yeah, because the scope is pretty large. But the other thing is like, since all the search doesn't go through the same nodes, it's not like having a central bottleneck, which is a server that receives all the requests and need to answer all of them. No, the requests are resolved by a bunch of nodes, so you can share the load of solving the requests, okay? But obviously, the scope is super large. The time may be quite long if you need to travel far away to a distant peer. And there's quite a high overhead due to the search, but as well due to the fact that the nodes may come and go, so it's totally dynamic. All right, so this is Gnutella. Then Kazaa came 1 year later, because you can see that Gnutella was running a little slow because of the overhead with the queries. And the idea here was also something that may be seen as similar to a list of candidate nodes. So what is the idea here? The idea is you need to join, but you don't join randomly some nodes. They introduce what they call the supernodes, okay? So a supernode is one of the nodes who have some good properties. And the good properties is the fact that it stays online long enough, it doesn't change IP so often, and is powerful enough to answer to the queries. So what it means here is when you join to one of the supernodes. The supernodes are in charge of a subgroup of all the peers, and the supernodes are connected together. All right. So what it means is when you join the supernode, you will publish your list of files to your supernode. So the supernode knows about all the files shared inside the same cluster. And when you want to do a search, first you send to your supernode, looks locally if the file is available. If it's not, then that query is sent to the other supernodes by flouting. But you see, as the number of supernodes is limited, you don't have the same problem that we used to have with Gnutella. And then you do the fetch by yourself. So once again, this is the architecture. So you need to first join one of those supernodes. So then the idea is, oh, but how can I know about the supernodes? Yeah, you may cheat by having a list of well-known supernodes in your system, which is outside the system of Kazaa. It's available on website. So you download this and you may join the system. So then you have clusters. So which means that you publish as well. So you join and you publish. So this guy knows about everything that is shared inside here. So if you have a request and you cannot find anybody sharing inside your cluster, you may flout the rest of the network looking for this until somebody, some other supernode, can find it locally in his cluster. So that was a pretty interesting idea. So you have two levels. At the top level, you have the supernode connected together with a mesh network. You flout the queries between the supernodes, but there are a few of them. And locally, each supernode is in charge of a limited number of nodes, okay? And everything happened locally, all right? Pretty interesting system, okay? And Skype have been designed the same way. So you know that before Microsoft took over Skype, there were no servers. So the supernodes were some well-known Skype clients running forever, like on the desktop that you never switch it off. But what happened with Microsoft, when they bought Skype, they replaced the supernodes with Microsoft servers to make it more scalable. There were a few examples where actually Skype was offline. Why? Because too many supernodes were actually not available. All right. So you may make it scalable and robust, but you never, I mean, depending on the graph that you have here, if you depend on some supernodes and those goes offline, that's a big issue. Okay? All right, so that was mainly the motivation for the supernodes. As you may see, that was whatever was new with Kazaa, okay? So once again, the query, as you may see, is limited in the scope. So you flout inside the clusters and you flout between the supernodes. So you limit the problem of flouting. And what is more, it takes less time to flout because the number of supernodes are limited, okay? So the supernode, the stability of the system was guaranteed by the fact that the supernodes were pretty stable. So they were quite often connected, okay? And one of the criteria they use is for how long in the past a node have been online. So you say, oh, this guy, since he never turned off his computer, So let's use him as a supernode. Okay. Okay, so if you don't have any further questions, we may continue with Bittorrent. I know that you have quite a lot of questions regarding Bittorrent. Can I follow up? So yeah, the three first architecture were pretty simple. I mean, pretty straightforward. It's not that hard to actually put in place. But BitTorrent was basically the state of the art, especially for large files. Right. So should I start with BitTorrent? Okay. So BitTorrent once again was introduced in 2002. So you see the story: Napster, then Gnutella, then Kazaa, then BitTorrent. So they've been it was quite an active area at that time, and it's mainly motivated by what we call the flash crowd. Okay, so what it means that I don't know, there's a new movie out, and everybody wants to watch this movie, or actually wants to download the movie. Okay? So the more people want to download, the more uploading speed you need. You need a system with a very large capacity, such as everybody can download the file. Right? So flash crowds are pretty popular on the internet. It happens quite often. It happened also back in 9/11 when everybody was trying to get news on CNN. So that's an example of flash crowds. So in the case of BitTorrent, we need to make it efficient, not for the search. So BitTorrent doesn't have search functionality. No way BitTorrent can tell you where to find the file. So you need to have the information from somewhere else. And what we want is to make it efficient to download a file that may be 4 gigabyte, 10 gigabyte for very large files. Okay. So the idea here is to say that you have one publisher. So somebody, a seeder, have the file first, and then you have many people downloading at the same time. Okay. And they want to avoid the freeloaders, which means that people who keep downloading without uploading anything. Okay, so the incentive here need to be high enough for people to share the bandwidth, to share pieces to others as well. So let's see. So first of all, we divide the large files in many pieces. Okay. And the idea is to say here that instead of looking for peers who have the whole file, which is quite, you shouldn't rely on this. You should make the best out of peers who has few pieces. So what you try to download is pieces. And you try to gather as many pieces as you can, such as you can reassemble them in a file. So yes, you're not looking for the file, but you look for pieces. So it makes a lot of difference, actually. We will see why it's so powerful. Okay. And once you have a piece, that's what you're going to use to trade with somebody else. So let's say I have piece 1. You don't have that piece, but you have the piece number 3. So then we can trade together, because you're going to send me the piece 3 only if I give you the piece number 1. Okay, so that's a trading system here where people are interested in each other because they have a piece that I'm looking for. All right. So remember about this. This is really important. And hopefully, after downloading all the pieces, so there may be a lot of them, right? Like 200 pieces you need to download separately. You may reassemble them to get the file. So that's very important. So what is interesting also having pieces, and that makes it super powerful, is the fact that you may downloading at the same time multiple pieces from different peers. So at some point, you may be downloading, let's say, 4 pieces from others for who you are actually sending a different piece that they're looking for. So, okay, so let's see the architecture, the overview here. Okay. So first of all, as we said, outside torrent, the first thing that I need to get is the so-called .torrent file. So why is it important? Because giving one file that you want to download, there will be a tracker. And the tracker is provided in this file. So here I will find the information regarding the tracker. So this is what we call the infrastructure node. Why? Because in order for the torrent to be able to be alive, you need to rely on one of those nodes. Okay? So that could be seen like a supernode. Locally, for one file that you are sharing. So the role of the tracker is the following. So once you extract the name of the tracker from the torrent file, so there are some well-known websites where you can download the torrent. You put the name of the movie, and then they will provide you with the .torrent file. So most of them, right, they only provide you with the torrent file. And you need the torrent file. Why? Because you need to know about the tracker. So the IP of the tracker is included here in the torrent. And so what you do, you connect to this guy, and what you're going to give him is your IP address, your port number, okay? And in return, he's going to provide you with a random list of peers. Not the complete list, but just a random list out of all the peers. Because you see, so if everybody first need to join this guy knows about all the peers in the system. And out of this complete list, you're going to receive a sub list of those peers. And what you're going to try to do now is, knowing this list, you will randomly select some of them, and you're going to start downloading. So let's take here a concrete example. So I have a file, it's divided in 4 pieces, the green, the blue, the red, and the yellow piece. And I have the choice in this system to download one of the pieces. If in the future I want to be able to trade as much as I can with others, I should have something that is very rare, that everybody is looking for. So in our case here, the green one would be much interesting, but probably the yellow should be the same, right? Yellow or green, it's probably the same. So I will do those ones. Why? Because they are not shared by many. So it means that in the future, I may have a very good leverage in order to obtain the other pieces. You understand? So yes, so the rarest is in case I'm selfish and I think about what should I do as a game for later. Okay, but we'll see that actually for the first one, we're not going to, that policy of the rarest, we're going to use for later. But for the first one, I'm not going to use the rarest. And the idea here is to say that if I start with the rarest, what may happen, if I don't have enough time to download it from a peer and I get ejected, right here, basically, don't let us complete the piece. I have an incomplete piece. And if it's the rarest, how can I complete that first piece? You see, the likelihood, if it's the first one, the rarest, to be able to complete that one is too risky. So if I cannot do the rarest, what do you suggest we should do? It's going to be the random. So I'm going to try to explain the random, why random is the best policy, all right? So let's go over. So this is what Bittorrent is doing. And by doing the right choice, that's why it makes it so powerful. So so what do we have? So a torrent is one session, and one session is only for one file. So for one file, you are going to have one torrent. And each torrent for separate files are independent. So it means that even though in your client, you may download different files, those are separate torrents. So you work with different set of peers. As we said, torrent is open. So it means that we have many clients, and you may connect to each other using different clients because the protocol is open, is standardized. So what is also very important, and we will see that later, even if you are a seeder, it doesn't provide any benefit in BitTorrent. So even once you complete downloading a file, even if you continue sharing the file once you finished, it doesn't provide any more incentive for other torrents. The incentive is within one torrent. So once again, you cannot localize the content. So you need to have the torrent file at the beginning, okay? And if it's not popular enough, so it's very powerful when the content is popular. And what do we mean by popular? It means that the more people downloading, the more powerful. Once people stop downloading and you don't have seeders, it's going to die. So to keep a torrent alive, you need to have many peers downloading at the same time. That's what makes it powerful. And that's the reason it's very popular. It's very good for flash browse. Okay? At some point, everybody wants to download the same movie. The more people, the more efficient. Okay? So anyway, so the torrent file, I don't want to get in all the details, but anyway, there are some key information like the length of the file that you want to download, MD5 hash of all of the content itself, and for each pieces, we have also a print hash for each piece. Why? Because we need to download if they are consistent. So in the torrent, once you download a piece, you run a SHA-1 hash and you check if it's consistent with what you were expecting, to avoid people from sending you like, crappy pieces, right? So you may flag a peer who just send you a piece that is not consistent with the one you were expecting, okay? The piece length, so yes, because they may be fixed, but you may have multiple sizes. And why do we need to have different sizes? Because since we need to list inside the file all the hash for all the pieces, the size of the file could be too big. So in order to reduce the size of the torrent file, we may increase the number of the pieces in order to have the size of one piece, in order to have less hashes listed in the file, right? So once again, we have the URL of the tracker, okay, and usually we connect through HTTP, so that's pretty simple. And some further information, such as whenever you download, you have some information like the torrent that has been created, who created that one, and so on. Okay, so then the tracker, as I said, this is the infrastructure node. We keep track of all the peers in the system, okay? The peers need to register. So the first thing that they need to do to arrive in the system is to register with the tracker. And you still communicate with the tracker quite often, at least to upload the list of pieces that you already have, okay? Because the tracker needs to know about what is your IP, your port number, but as well what are the pieces that you are currently holding. The tracker will also make a selection. As I said, it will send you a random list of the peers, okay? Once again, the peer is not involved in downloading pieces. So each peer in the system have an ID, okay? So this is basically the name of the client. And usually, most of the time, what it does, it have a random value, which is like the IP address plus the clock system when you join and start running as a peer. So that gives you a random ID that is unique inside the peer. One of the problems with this is the fact that if you leave the torrent and you change your ID will change, and it's like starting from scratch, since the tracker won't have any recollection of you, right? Or other peers won't know you again. So it's really bad, because if you leave, you change your ID. To bootstrap, as I said, so you need to download the torrent file, okay? You retrieve the URL of the tracker, and then you connect using HTTP with the tracker, so it's pretty standard. And what you send to the peer is, once again, your ID, yes, some info with a key, whatever, the client, the list of peer that you want, which is limited to 50 by default, and some statistics regarding your peer. Then the tracker will return, if any case you have a failure, whatever, some statistic, but that does it regularly, plus the random list of peers that you were asking. And normally it's a list of 50 peers. That's it. You cannot learn about any other peers. What's going to happen is, out of those 50, you're going to create 40 TCP connections to 40 of them. Okay? But be careful. Those connections, you don't use them in order to send or receive pieces. You have a connection to 40 of them, and you may choose to download or upload to very few of them. But what's going to happen, you're going to make a kind of a selection process, and we will see that depending on the clients, you may only be in relationship with 5 or 6 of them. That's it. The rest of them, you keep the TCP connection running, and that's it. So in total, it means that in your network, since you are connected to 40 of them and other peers to 40 others, so you have 40 ingoing and outgoing, in total, you have 80 connections. You see, because peers doesn't have to reciprocate with you. So you may be connected to someone and somebody else will connect to somebody else. So it gives you like 80 connections. So this is really, really a robust graph because it's totally random, right? So even if you lose some peers, it doesn't matter that much. You still have 80 connections. So you see, super robust. So yeah, okay, well, we have chunks. I don't want to get into those details. So the most important is the peer selection. So it means that out of all the peers, you need to find peers who you're going to send to the pieces while preventing the free riders. So it means that I want to make sure that when I'm sending to someone, I'm receiving something in return. And the selection here is based on the ratio. So which means that if I compare my uploading to my downloading rate, we want UD to be always close to 1. This is a magical number here. So, and you see that in this incentive means that the faster I'm going to upload, the more bytes I'm going to download. And if both we're doing the same, we're going to be happy about this, and we're going to keep exchanging pieces together. So yes, the selection of a peer is based on the downloading rate compared to my uploading rate. Very simple. Then we have the chunk selection. It's like the piece selection, whatever. I don't want to get into the details. And in order to select the chunk, so let's say you have peers, and those peers have some pieces, I need to select which piece should I download. So they have a list of 10 pieces. I need out of this list to decide which one should I choose. I still have the choice of which one I'm going to download, right? So we will see that there are multiple strategies. So random and reversed. We're going to see that actually we're using both. The first piece that I'm going to use is random. For the following pieces, I'm going to use the reverse, but it's only the local, because I cannot know which one, if it's the reverse inside my torrent is impossible. So usually what we do, we always first do the selection of the peer. That comes first. And once I know the good peers that I'm connected to, then I'm going to select a piece that is shared by those peers. So I always, prefer to select the peer and then the piece, and not the opposite. Why? Because here, obviously, the torrent depends on the capacity of the system. So I'd rather have a system where I maximize the capacity by selecting the right peer instead of taking a chunk, but from a very poor sender who's going to slow down my torrent. Okay, so first the peer and then the chunk. So once again, the peer selection that comes first. Once again, we do that based on what? On the uploading bandwidth. So we always favor the neighbors who can upload at the highest rate. Okay. And so what we do, so let's say we already said that we have who maintain the tracker. That's a good question. We shouldn't answer this question. It's not legal. So whoever is maintaining this is hiding well. All right. So, okay, Yuchan. So let's say, so I have 1, 2, 3, 4, and 5. So the idea here is to maintain this list. And what I do, I upload to them all. And for 10 seconds, I'm going to measure how much do I receive in return. And if after 10 seconds, I'm not happy, means that UD is different from 1. In that case, I'm going to remove the peer that doesn't provide me with the same downloading rate compared to my uploading rate, and I'm going to switch to another one out of the list of the 50 peers that I have. So you see, so this is like cycles. So every 10 seconds, I may change the peer because I'm looking for a good peer who's going to provide me with this. All right. So which means that once I select such a peer, I may stick with him until we can exchange the pieces. But once the pieces are not interesting enough to me, I may switch to another peer. All right. This is just a random change. What do you mean random change? Oh, yes, Gabby. Yeah. It's randomly you're going to jump to another peer. All right. So what you need to understand is as well, out of those, we also have the special case of this peer. So every 30 seconds, I will choose one peer who I will decide to upload without asking anything in return. So the rationale here, there are two rationales why we may want to send without asking anything in return. First of all, this guy may be first joining the peer, the BitTorrent. So how can I start up if I cannot get a piece because I have nothing to give in return? So that's the reason all peers in the system should always allow for 30 seconds out of the 5 here. I took an example with 5, could be 6, it depends on the client. But out of the list of my 5 peers that I'm sending to, one of them, I don't ask anything in return for 30 seconds. So the rationale here is this guy may bootstrap by getting a first piece. And the second thing, it may help me to discover that this guy actually is uploading super fast. So if he's uploading super fast, it may be a good peer for the future. So it's also a good way here of discovering other peers in the system. So it means that if after 10 seconds, this guy has been removed, maybe this one can be the good one by sending me with a good uploading way. So this is dynamic. So every 10 seconds, I change the people who I'm downloading from, especially if I can not get the good ratio between the U and the D. All right. So 2 types of nodes. All right. Okay. So then we have the last question is which chunk should we, or which piece should we download? So as I said, we have multiple different policies. Okay. So obviously the local rarest seems to be the most obvious for a peer, but this is too dangerous to select this from the beginning. So that's the reason we're going to use for the first chunk, we're going to take a random chunk, and later we're going to take the rarest. So first we take a random chunk, and then we start measuring how popular is this chunk, and I'm always going to take the rarest one. So nowadays, BitTorrent is very powerful. Why? Because it accounts for more than 30% of all the traffic on the internet. Okay. There are also some companies using BitTorrent for their own usage. For instance, if you take Twitter, Twitter have multiple servers, okay, across the world. So to synchronize the servers of Twitter, they're using BitTorrent because they have huge amount of data that need to synchronize to all the servers, like the tweets or whatever. So in order to synchronize, they use their own version of BitTorrent between the servers. Okay. So of course, we still have the problem of the content that are not really popular, because as we said, you see the system is really have a high capacity as long as you have peers who are downloading. If you reduce the number of people interested in a file, you're going to have a very poor capacity in your system. All right. So there are still some legal aspects, and that's the reason I don't have the detail to get into a court to see how we may remove the use of the torrent. So I'll let you read about the court here. I'm going to jump to the overlay. So guys, for those who are reading from the PDF, I'm going to just talk about the tunnels, a quick introduction, because in the assignment that you have, there's a quick question on this. All right. So what do I mean by overlay networks? So they are pretty important. And they explain as well the fact that, as I said, in a peer-to-peer system, nodes are connected together by a TCP connection. So what do I mean by that? So let me take an example. Maybe it's going to be much better. Okay, so let's take this architecture here. So what do we have? Here we have a router, okay, 2 routers, and in the middle, I'm going to have a tunnel. So the tunnel could be seen as a VPN. So the idea here is to say that locally here, I have a packet, okay? And what I'm going to do when I'm going to go through the router is I'm going to have an extra header. And this header, I'm going to hide the detail of the initial packet. So you see, so because of this sublayer here, is that I'm introducing an extra layer. And who said layer? Said extra header. And the idea of this header is to say that now, if I look in the middle of the network, all I see is that header. I don't see any other details. Why? Because what I may do as well is to say that, oh, I'm going to encrypt this packet. I'm going to put a cipher, such as I don't need any of those information. So then the packet going to be received by the router. The router going to remove the header, going to decipher the packet that was inside, and look into the content and say that, oh, this packet needs to go to B. And then you send it to B. Okay? I'm sorry, the animation was wrong. You understand what is about doing a tunnel? So the tunnel means that at the entry of the tunnel, you add a sublayer, which is going to add a new header to your packet, an extra header. All your packet going to be processed in the network based on this outer header that is removed at the end of the tunnel. And that's it. So this is pretty interesting. Okay? So so anyway, so what is happening here is pretty much similar to what we do with existing layers. So for instance, you remember that we have the MAC layer, we have the IP layer, and the packet, in the IP packet, what do I have? I have the sender and the destination. The header doesn't change, but needs to go through different hops. So to specify to which hop need the packet to go through, I'm adding here the layer 2 header that indicates that, oh, okay, this packet need to go to R1. Once I reach R1 gonna look inside the packet header. He can see that, oh, B is the destination, so the packet need to go to R2, and so forth. So you see, so basically each layer adds a header. Each header have their own purpose. So if I look at what I have now with a tunnel, so normally my packet is supposed to look this way. So the packet is encapsulated such as I indicate that from A, it needs to go to the next hop, which is R1. Now, because R1 is at the entry point of my tunnel, I'm gonna add an extra header in the middle, which is a gray header that you may see here. So this needs to go through R2, but the decision to go through R2 is based on this new header, because this one here is totally hidden. The network won't look into this header. So it's like when you go to the mail, you can put an envelope inside another one. So the outer envelope is the one you look. Once you get to the first destination, you open the envelope, you look inside, and you know about the second part of the path. This is pretty much the same here, okay? So what is interesting with doing VPNs, doing tunnels, we can do VPNs, right? What do I mean? I mean that the packet needs to get encapsulated, and the packet here you see have been encrypted. So all the information have been encrypted. Why? Because you route the packet based on the outer header that have been added at the entrance of your tunnel and at the exit of your tunnel when you remove it, okay? So you need to see now that we may have multiple headers depending on how many tunnels we go through. So let's say I have one router here, I have a first tunnel, and here I have another tunnel. So this is R1, this is R2, this is R3, this is R4. And as you may see, the packet gonna arrive from A, goes here, go through this tunnel, go outside this tunnel, and go to B, okay? So how many headers do, so first of all, the packet here gonna be A to B. So now when I reach the first entry point here at R1, I'm gonna add a new header. So here I'm gonna have AB. And from what is the new header that I'm gonna add? Can you give me the names of the routers, the entry and the exit for this tunnel? All right. Yeah, super good answer. All right. And now if I go through the blue one, so it means that you see that the header is still in place. So I still have L1, L4. And inside, I have A and B. And now, on top of this, I'm going to add another header because I have an extra tunnel inside the tunnel, which header? Yes. So you see, so you may add as many as you want. You see? So no limit. So from one tunnel, you can go to another. All right? Okay, guys. So keep this example. You can even take a screenshot because the last question of the assignment will be based on this. Even though for this assignment, you have till Friday after the break to take it. All right. So that was about the overlay networks. Quick one. So once again, as a conclusion, right? So we have peer-to-peer networks where nodes are end hosts, all right? So primary, they were only for file sharing and also with Skype for voice over IP. We saw three main approaches depending on the function, which is either the join, the publish, the registration, the queries, and the fetching. And all of those functions need to be implemented. So you can either do a centralized one or distributed one. So we saw that Napster, only the fetching is peer-to-peer. With Gnutella, everything is distributed. And with Kazaa, we have a hybrid version of this. Bittorrent is for very large files. So the idea here is divide in chunks, download at the same time for multiple peers, and provide incentive by doing a selection of the peers, such as they send with the same speed as they download. You have a question in the assignment regarding this with few examples of a peer system with 6 peers. All right. So peer-to-peer is very interesting because this was the first time that when we saw the first application, those were Napster. Napster was the very first application that thought about saying, well, client server sucks because we don't have any way of finding a server if it's not an official one. So doing peer-to-peer was very interesting. And from now on, yeah, a lot of companies are starting using this, even though those are not for some illegal reasons. All right.